When we have a chemical reaction, when we write it like this, it doesn't really tell us anything about how much is produced, or how to what extent this reaction goes to completion. Okay, we might assume from looking at this that if we start with 1 mole of nitrogen and react that with 1 mole of oxygen, or combine that with 1 mole of oxygen, that it will react and form 2 moles of nitrogen monoxide. But in fact, that's not the case, and we can be thankful for that, because these are the main two components of air, and we don't want them to produce nitrogen monoxide, which is an air pollutant. Okay, so this reaction does proceed to a certain extent, a very limited extent, but we don't know how much. Okay, there's resistance, if you will, to the production of nitrogen monoxide. All right, and so the way we tackle a problem like this is we introduce the concept of an equilibrium. Okay, an equilibrium is essentially saying, yeah, there's a certain amount of product or products that are produced, but it's not complete. All right, so there's still reactants that are left over, and quite often it's the vast majority that are left over and only a tiny bit are produced. Or maybe it's the other way around, where there's just a tiny bit left over and the majority are produced. Okay, there's anywhere in between. Some are almost 50-50 between reactants and products. But the thing is, we have both reactants and products. All right, so instead of writing the arrow just in one direction, we write it in both directions. Okay, and this way we have the indication that there's also the reverse direction. Okay, and this is true for systems that are reversible. Okay, that means I can react these and produce the NO, or the NO can break down into the nitrogen and oxygen. Right? So in other words, what I do to produce this, to produce my products, I can undo and end up with my reactants. That's the concept of reversibility, and it's quite prevalent in chemistry. Okay, so now the question is, how do we express the extent to which this reaction goes to completion? Right? The way we do that is we use what we call an equilibrium constant. We give it the abbreviation K, capital K, and we determine that constant by taking the number of product molecules, the concentration of each of those, divided by the concentration of the reactant molecules. Okay, so concentration we denote by square brackets, and we put the concentration of the products divided by the concentration of the reactants, and we're going to multiply those. Okay, so concentration of nitrogen times the concentration of oxygen. Okay, now the thing is, we have to take these coefficients into account, and the way we do that is by raising it to the power of the coefficient for each of these. Now the nitrogen and oxygen are 1, so we don't show that, but the NO has a coefficient of 2, so we square that. All right, so this gives us then essentially a measurement for the balance between reactants and products, where if we have a value greater than 1, it's telling us that NO squared is greater than N2 times O2, right? Because if you have a smaller value on the bottom, when you divide that fraction, you get a number greater than 1. If you have a number less than 1, it tells us that we have fewer products, or a smaller number up here, divided by a larger number. because a smaller divided by a larger number gives us a value less than 1. Okay, so that gives us an indication of how far to each direction depending on how much greater than 1 or how much less than 1. Okay, so if we look at the K for this particular reaction, at room temperature, its value is 4.5 times 10 to the negative 31st. Okay, now you'll notice our units here would be molarity squared divided by molarity times molarity, so they would all cancel out. It doesn't always happen. Most of the time with equilibrium constants, we just reference the value. Don't concern ourselves so much with the units because it just kind of complicates things. Sometimes, however, we do have to pay attention because you'll notice this particular reaction is a gaseous reaction. And often with gaseous reactions, it's more convenient to express it in terms of pressures. And we can do that. We can use a Kp, okay, we use a subscript P to indicate pressure, and sometimes we'll put a subscript C to indicate concentration. So if we say Kc, then we know we're talking about the concentrations of those gases. If it's Kp, then it would be the partial pressure for each gas. Still, the NO would be squared, and the nitrogen and the oxygen, it would all be in the same arrangement, just talking about the pressures. But the value would be different because it would have different units. So you just have to be aware of that. Most of the time, especially with aqueous systems, we're dealing with concentrations.